Welcome back, Dr. Tullis here. We are looking at section 2, looking at reaction conditions and rates of reactions. We just got done looking at chemical kinetics and how it's the study of reaction rates, how reaction rates change under varying conditions, and what molecular events occur during the overall reaction. But there's several factors like the reactant concentrations, the temperature, the presence of a catalyst, and even the surface area of a solid reactant or catalyst that all affect the rate of a reaction. Let's look at the first one, the concentration of the reactants. More often than not, the rate of the reaction increases when the concentration of the reactant is increased. We know that concentrations is measured in moles per liter. Moles tells us how many particles, right? If I have 1 mole versus 2 mole, that means I have 6.02 times 10 to the 23rd more particles in that substance. And if I have 4 moles per liter as opposed to 8 moles per liter, I have a greater population of reactants. So when I increase the population of the reactants, we're increasing the likelihood of successful collisions, of them bombarding one another and reacting. In some reactions, however, the rate is unaffected by the concentration of a particular reactant as long as it is present at some concentration. However, here is an example when I have magnesium metal added to hydrochloric acid, and notice I have 2 different concentrations. I have 0.3 molar and I have 6 molar. And we can see that the 6 molar solution occurs very quickly. The 0.3 molar takes about 400 seconds. So the greater the concentration, the faster the rate is. I can also have a catalyst that can affect reaction rates. A catalyst is a substance that increases the rate of a reaction without being consumed. So it's not a reactant, it's not in the products, it's not consumed in that overall reaction. The catalyst generally does not appear in the overall balanced chemical equation, but it usually is indicated by writing what that catalyst is over the arrow. So here's an example of having hydrogen peroxide decomposing into liquid water and oxygen gas. It can happen naturally. And if I were to draw an energy level diagram, here's my reactants, my H2O2, and there's an activation barrier, and it will eventually create my products. These are my products, this is my reactants, and that reaction will occur. However, when manganese dioxide is added to the hydrogen peroxide, that catalyst makes that activation energy lower so that the reaction can happen more quickly. It's still starting with the same reactants, it's still getting us to the same products, it's just changing the pathway. Instead of having to go all the way up here to reach this activation energy, we're able to take a shortcut to get to our products. So that catalyst speeds up reactions by reducing that activation energy needed for a successful reaction. The catalyst may also provide an alternative mechanism or pathway that results in the faster rate, just like I showed above. Temperature also affects reactions. Usually reactions speed up when the temperature increases. A good rule of thumb is that reactions approximately double in rate with a 10 degrees Celsius rise in temperature. Also, number 4, we can look at the surface area of a solid reactant or catalyst and the physical state of reactants. Only molecules at the surface of a solid can come in contact with other reactants. The smaller the particles of a solid, the more molecules are found on that solid's surface. So with really small particles, the effective surface area on the rate can be quite dramatic. Farmers know that fine dust particles that are suspended in the air used for grain storage, like in a silo or a feed mill, can represent a major explosion hazard. This picture shows us that I might have a pile of a solid here with a torch on it, and it's going to have a difficult time burning, but when it's in a fine powder, it's going to combust quite rapidly. If you want to pause the video here to have a little summary over the factors that affect reaction rates, you might find it helpful. In this section, we're going to dive a little deeper looking at the effective concentration on reaction rates. One important goal in studying kinetics of a reaction is to determine its mechanism, that is, how the reaction occurs at the molecular level. The place to begin is to learn by experiment how reaction concentrations affect the reaction rate. The key word here is by experiment. The resulting relationship between reactant concentrations and reaction rate is expressed by an equation called a rate equation or a rate law. To obtain the rate of a reaction, you must determine the concentration of a reactant or product during the course of the reaction. And this is during the experiment, so we have to experimentally determine this. One method for slow reactions is to withdraw samples from the reaction vessel at various times and then analyze them. More convenient are techniques that continuously monitor the progress of a reaction based on some physical property of the system. Two properties used are gas phase partial pressures and colorimetry. We will just cover these real quick, but in gas phase partial pressures, you're able to follow the pressure change as the reaction proceeds, and then you can obtain the reaction rate. Here's an example where I have dinitrogen pentoxide crystals. They are sealed in a vessel that has a manometer, and it's heated to 45 degrees Celsius. The crystals will vaporize, and the N2O5 gas decomposes. Manometer readings provide the concentration of N2O5 during the course of the reaction based on partial pressures. Another means that we're able to measure during the reaction is colorimetry. By following the reaction color as the reaction proceeds, you can obtain the reaction rate. The color is equal to the absorption of light by some species. Here's an example looking at the reaction of hypochlorite ion with iodide. The ion, IO, absorbs near 400 nanometers, and the intensity of the absorption is proportional to the concentration of that ion. Then you can use the absorption rate to determine the reaction rate. Let's look at that dinitrogen pentoxide reaction here. The effect of concentration can be determined by evaluating how the rate is affected when the concentrations of the reactants are varied. Here I have 1 molar concentration and 0.5 molar concentration. So we doubled the concentration from 0.5 to 1, and it doubled the reaction rate. We went through and experimentally measured after 1 hour, 2 hours, 3 hours, 4 hours, the concentration of N2O5 when it was a 1 molar solution and when it was a 0.5 molar solution. And we were able to then measure the rate of the reaction like we did in section 1, and we were able to see that by doubling the concentration, it doubled the rate. We have 0.24 molarity per hour as opposed to 0.12 molarity per hour. From this, we know that the rate of this reaction must be directly proportional to the concentration of N2O5. So we use this symbol to show that the rate of the reaction is directly proportional to the concentration of N2O5. This proportionality is expressed by the rate equation. When we write a rate law or a rate equation, we have our reaction here, and this is what it would look like. The rate law would take the following form. We would say the rate of the reaction is equal to K. We use a proportionality constant. It's called our rate constant. This rate equation tells us that the reaction rate is proportional to the concentration of the reactant. Again, we only are looking at reactants. Notice that the concentration of A and the concentration of B are both of my reactants. I don't have X in my rate law because we're only looking at that reactant. Now we do have some superscripts here. We have M and N. Notice those are not the stoichiometric coefficients. The exponents M and N are the reaction orders, which we'll get to in just a minute. But those reaction orders, those superscripts can be 0, 1, 2, fractions, or a negative number. The concentration of a reactant with a 0 order dependence has no effect on the reaction rate. These numbers, the 0, 1, 2, they must be determined by experiment. Cannot be obtained by simply looking at the balanced equations. Don't think that you could go, if this was 3A and 2B, blah, blah, blah. Don't think that that A would be cubed and the B would be squared. No. You cannot tell those orders by looking at that balanced equation. We have to look at the experimental data. So if you were told to write the rate law for this reaction, we can only do part of the rate law. We would say that the rate of the reaction is equal to K times the concentration of my reactants are hydrogen and NO. So I would say concentration of H2 and the concentration of NO, but I don't know those superscripts. X and Y are orders of reactants that we have to look at experimental data in order to get. So again, I can't stress this enough. Those are experimentally determined. We'll find those out in just a minute. We'll do some practice. If we wanted to know the overall order for our reaction, that is equal to the sum of the orders of our reacting species in the rate law. For example, if I look down here at this equation, we found experimentally that our rate law was reaction rate is equal to K times my reactants are NO. So I'm going to say concentration of NO. From experimental data, we saw that it was to the second order. Our second reactant is chlorine. Experimentally, we found that it must be to the first order because there's nothing written there. This is second order in regards to NO, first order in regards to chlorine. So 2 plus 1 is third order overall. Here's another one. I have nitric oxide reacting with hydrogen. So nitric oxide and hydrogen are my two reactants. So in my rate law, I would say that rate is equal to K times the concentration of NO times the concentration of hydrogen. And experimentally, we were able to find that NO was to the second order. Hydrogen is obviously to the first order, since nothing was written next to it. So second order in NO, first order in H2. 2 plus 1 is third order overall. Let's look at the rate constant, that K. Let's say that I have a reaction X plus Y to give me XY. I would write my rate reaction is rate is equal to K times the concentration of my one reactant times the other reactant. And let's just say experimentally those were both to the first order. So 1 plus 1 is second order overall. So this would be a second order reaction. Reaction rates have units of moles per liter over time. So molarity over time. When concentrations are given as moles per liter. Rate constants must have units that are consistent with the units for the other terms in the rate equation. Now, time could be in seconds, minutes, hours, days, years, whatever. So if I had a second order reaction, my K constant would be liters over moles, and then the time, whatever the reaction was measured in seconds, minutes, hours, days. If I had a first order reaction, my units of K would be 1 over seconds, or 1 over minutes, 1 over hours. If I had a zero order reaction, my K units would be moles per liter over time. Now, how do we find those reaction orders? We're going to use something called the method of initial rates. This is when we run the experiment multiple times, and each time we're going to vary the concentration of only one reactant and measure its initial rate. The result change in rate indicates the order with respect to that reactant. And for these problems, you're going to see a table with lots of data in it. Now, when we are looking at that data, if we double the concentration and it doubles the effect of the rate, this would be a first order dependence. And here's how I like to write it. If I double the concentration and it doubles the rate, 2 raised to the what power gives me 2. That would be to the first power. That's why it's a first order dependency. Now if I double the concentration, so 2, double the concentration, so that my concentration I just have on the left, and it quadruples the rate, 2 raised to the what power gives me 4, and that would be 2. So that would be a second order dependence. If I double the concentration, so put a 2 here, concentration's on my left side, and it makes my rate increase by 8, then 2 raised to the what power is 8, and that would be 3. Now what if I double the concentration? So I had double the concentration, but my rate doesn't change. So my rate stays the same. We would put a 1. It's not going to double it. So I wouldn't put a 2. It's not going to triple it. I'm not going to put a 3. It's not going to make it increase by 8. I'm not going to put an 8. It's going to stay the same. I'd put a 1. 2 raised to the 0 power would be 1. So that would be a 0 order dependence. Let's look at this reaction here. I have NO reacting with chlorine to give me NOCl. We know that we can write our rate reaction, our rate law, by saying that rate is equal to K times, we've got the concentration of NO, we don't know what that exponent is, times the concentration of chlorine 2, we don't know what that exponent is. But now over here to the right, we've got experimental data. Let's first look at experiments 1 and 2. And the reason why I'm choosing 1 and 2 is because in 1 and 2, notice that my chlorine concentration stays the same. There is no change in chlorine. So I can focus on what is happening with NO. And NO changes. So I'm going to focus on experiments 1 and 2. How do I figure out how much it changed? Well, I'm going to take experiment 2, since it's a larger number than experiment 1, 0.5 over 0.25. I'm going to divide 0.5 divided by 2.5, and I see that it's 2. So going from 0.25 to 0.5 doubles the concentration. We're looking at concentrations here. So remember when I put my concentration on the left, I'm going to say 2 because it doubled. 2 is equal to, let's see what happened to the rate when I doubled NO's concentration. I'm going to take my rate from trial 2 and divide it by my rate from trial 1, and I see that it quadrupled. So 2 raised to the what power is 4? Well, that would be to the second power. So NO is a second order reaction. I can write that just like this, NO squared. Now I need to find when NO stays the same, just like chlorine stayed the same in these two trials. Now I need to find two trials where NO stays the same and chlorine changes. Now let's look at experiments 1 and 3. Notice that if I look at experiment 1 and experiment 3, concentration of NO stays the same, 0.25 and 0.25, when the concentration of chlorine went from 0.25 to 0.5. So the concentration of chlorine now doubled, so I'm going to put a 2 here. And when the concentration of chlorine doubled, let's see what happened to the rate from 1 to 3. 1.43 times 10 to the negative 6, and it went to 2.86 times 10 to the negative 6. So when I doubled the concentration of chlorine, it doubled the reaction rate. So 2 raised to the what power is 2? That would be 1. So it's first order with respect to the chlorine. So I can write my reaction rate just like I did up above to show that my reaction rate is equal to K times the concentration of NO to the second order times Cl2. 2 plus 1 is 3. This is a third order reaction overall. And then I can even go one step further and solve for K, for this reaction rate constant, simply by taking any one of these trials, and I like to just use trial 1 because it's the first one listed. I'm going to plug in the concentration for NO into my NO, put the concentration of chlorine into chlorine, and take that reaction rate and put it in for reaction rate. So my only unknown is K. So if I plug in my reaction rate for 1, my concentration, I solve for K, and I would get 9.15 times 10 to the negative 5th. And for a third order reaction, my units would be liters squared over moles squared per second. Let's look at another example. I've got this reaction between carbon monoxide and nitrogen dioxide, and we are looking at the concentrations of both of those reactants in experiment 1, 2, 3, 4, 5. So let's find an experiment where carbon monoxide stays the same, and I could look at 1 and 2, or 2 and 3, or 1 and 3, doesn't matter. I'll just pick 1 and 2 because they are the first two where carbon monoxide stays the same. So when that stays the same, we're going to look at what happens to NO2. I went from 0.35 to 0.7. That doubled. What happened to the rate? When the concentration doubled, 3.4 to 6.8, it also doubled. So 2 raised to the 1 power would give me a first order rate for NO2. So I'm going to put a 1 here for a minute. Now let's find the carbon monoxide. So we want somewhere where NO2 stays the same. And I'm just going to look down here, experiments 4 and 5. This stays the same. So what happened to go from 1.02 to 1.53? That's not a double, but it's not staying the same. So I'm going to take 1.53 and divide it by 1.02 and see, oh, that multiplied by 1.5. All right, so I increased this by 1.5. So what happened to the rate? I'm going to take 10.2 divided by 6.8, and I also got 1.5. So 1.5 raised to the what is 1.5? Well, that also would be to the 1. So I'm going to write my reaction rate as reaction rate is equal to K times CO, that's to the first order, times the concentration of NO2 raised to the first order. And in order to find the rate constant, we can use any of those experiments and just plug in that experiment number's rate into there and the concentration of both of those reactants there to solve for K. Let's try trial 1. We were told that its rate was 3.4 times 10 to the negative 8. I'm going to go back here just to show you. 3.4 times 10 to the 8 was our initial rate. Our concentration of CO, we're going to use 5.10 times 10 to the negative 4. NO2, we're going to use 0.350 times 10 to the negative 4. So that's my concentration for the CO. There's the NO2. There is my rate. I'm going to multiply these two together and then divide both sides by that answer. And I got K is 1.9 liters over moles hours. This is a first order, so a second order overall. Here's an experiment where we looked at nitrogen monoxide reacting with oxygen. Here's our reaction. And we measured various initial concentrations of NO and O2 in 5 different experiments. See if you can determine the rate equation from this data. What's the value of the rate constant K, and what are the units? Why don't you pause the video here and see if you can do what we did the last example. Okay, let's look at experiment 1 and 2. I can see that by looking at 1 and 2, NO stayed the same. Great. While it stayed the same, then let's analyze what happened to oxygen. Oxygen's concentration went from 0.01 to 0.02, so oxygen's concentration doubled. What happened to the rate when we doubled oxygen's concentration to go from 0.028 to 0.057? Well, I can't do that in my head, so I'm going to use a calculator and do 0.057 divided by 0.028, and that is doubling my rate. So 2 raised to the 1, that'd be a first order reaction for oxygen. Let's try to find for NO. We want to find 2 experiments where oxygen's concentration stays the same and NO's concentration changes. So we can see by looking at this that 0.02 and 0.02, okay, it stays the same there and there. Which one should we look at? Well, if I compared these two, does the concentration of NO change? Oh, yes, it does. Okay, so we're going to look at 2 and 4. 0.02, 0.02, so this stays the same. 0.02 to 0.04, that's doubling NO's concentration. Let's see what happens to the rate. So 0.227 divided by 0.057 is 4. So 2 raised to the second power, so it would be a second order with respect to NO, first order with respect to oxygen. So my rate law would be rate is equal to K times NO to the second order times oxygen to the first order. We're going to use data. We just chose experiment 1, so I'm going to put in the rate from experiment 1, the concentrations from experiment 1, square my 0.02, times it by 0.01, divide both sides by my answer, and I would get K is equal to 7.0 times 10 to the third liters squared per mole squared seconds. Here's a pretend equation with some pretend data. See if you can determine the rate law from this reaction and calculate the value of K. If you looked, we should get first order with regards to C and third order with respect to D, and our K value, if we plugged in experiment 1 or 2 or 3 or 4, whatever, we would get 0.625 inverse seconds inverse molarity. Why don't you try this one? The reaction is second order NO, third order overall. The rate law for the reaction is what? Hopefully you got this for your answer. One more. Should have gotten 25. Take a second to look at the summary, and we will move on to section 4 next.